Hello, welcome to my Physics 2212 lab. This is lab 3 on magnetic fields from permanent dipoles. So here's the table of contents. So the purpose of this lab is we're going to measure the distance dependence of the magnetic field due to a small body magnet, and then we're going to compare our measurements to the values calculated through the equations that are defined by Biot-Savart law. To measure the magnetic field of a permanent dipole magnet, we're going to utilize a magnetometer app for phones to track the magnetic field. So the concepts that we're going to discuss first with the magnetic constant, which goes into the Biot-Savart law equations. That's 1 times 10 to the negative 7. We have Biot-Savart law itself, which is B equals magnetic field times QV cross R hat over R squared. That is a general equation for calculating the magnetic field at various points around a magnetic dipole. We have the magnetic dipoles themselves, which are just objects that have a north and south pole and create a magnetic field around them. We have on and off axis magnetic fields. These are just the various ways we can calculate a magnetic field if it's on or off the axis. So if it's perpendicular to the axis, on or perpendicular on axis, we have magnetic constant times 2 times mu over r cubed. Mu is the dipole moment. And then if it's perpendicular to the dipole on a perpendicular axis, we have B perp equals magnetic constant times mu over r cubed. Again, mu is a magnetic dipole moment. And then we also have off-axis magnetic field calculations, which is the magnetic constant times 1 over r cubed times 3 times mu dot r hat times r hat minus mu. And again, that mu is the magnetic dipole moment. And then we have linearization and distance dependence, which in our lab, we used those two concepts to calculate the magnetic dipole moment, which allowed us to calculate the magnetic field at various points within it. And then we have Earth's magnetic field, which is very important because that plays a role in the actual numbers that we get within our calculations, and we have to account for that. Now we're into systems and surroundings. So the system is the permanent magnetic dipole itself, and then the magnetometer that within the phone that we're using to calculate the field. Then we have the surroundings, which are surrounding magnetic fields, such as random electrical and magnetic devices that might have residual magnetic fields in the area, or most notably the Earth's magnetic field. For initial conditions, we have the magnetic field due to Earth and Atlanta, which is 49 microteslas, and then we have the various distances that we're calculating using various different microtesla magnetic field amounts. So then we have the preview of the results. Our intercept was k equals 4.004 times 10 to the negative 6, and our distance dependence is n equals negative 1.3849. Those are both calculated from linearization. And using those values, we calculated the magnetic dipole moment and found that is 0.6002. So in the experiment, tape was used to locate the phone's magnetometer. The magnetometer was then placed at various distances away. We determined how far away from the magnet certain magnetic field magnitudes were reached, and we incorporated on-axis and off-axis components into the experiment. And so this is some more data. Let's see more of it. This is all the experimental data we gained from this experiment. We have the various different magnetic field amounts, and then we have the distances that we got those at. We have an actual linearization graph here, which gives us the K and the N. And then we have our off-axis field calculations, which includes dperp by Earth, all the various B, X, Y, Z stuff, and then the magnetic field net. Here are the calculations that we used for our simulation following the experiment. We have our calculations towards the top that show how we calculated n and k, and then also we showed how we get the mu, the equation that we're using, and we also used n and k to figure out what r is, and then after having n, k, and r, we put all of those into our calculation for mu, and we got the 0.6002 figure. Here's our code for the experiment. As you can see, we have mu over here. We have the actual dipole calculation for the magnetic field. We have a scale, we have the distance, and we have the various different axes and perps that we used to go into our different area equations. And then we also have, finally, down here, the calculation for the 45-degree arrow using all this data and using dperp. And as you can see, this is what we have here, and this is the data we gained from it. So some similarities and differences we saw between the experiment and the simulation were that they had a similar order of magnitude and the results were fairly similar, but both had room for various forms of error, and then the differences were mainly in that form of error. We had more room for human error in the experiment, and then the computer simulation was predicting through linearization, which in itself could result in error as it's not an actual observed experiment. So the possible sources of error that we had in general were outside interference from various nearby electrical and magnetic equipment. We had failure to compensate for Earth's magnetic field, just various forms of human error, outside interference from nearby steel or other or metal, and accidentally bumping the smartphone. So some discussions, questions we had were if we hadn't oriented the experiment to compensate for magnetic north, what would change? If we hadn't oriented to compensate for magnetic north, we would have saw that the measurements would be completely off, and that would result in drastically different outcomes in our simulation versus our experiment. And also incorporating the magnetic field of Earth into that net magnetic field because we didn't compensate for it would result in a magnet that appears much stronger or weaker depending on the way we orient everything. And so if we were to stick two identical magnets together and to end, what would happen? Well, it's simply just the magnetic field would become stronger. The directions at every point would stay the same. It's just that we double the magnitude at every point. So these are our conclusions. We calculated the intercept and distance dependence, which are there through linearization, and that results in us getting a magnetic dipole moment of 0.6002. And using all of these different values that we gained from our calculations, we threw that into the simulation. And from the simulation, we calculated V to be at 45 degrees at a distance d from the magnet at 1.72 times 10 to the negative 6 at the x direction and 5.16 times 10 to the negative 6 at the y direction. And this was fairly similar to what we saw from the experiment. That is everything in our lab. Thank you for watching.